Hi everyone, I'm Shulei from the Ohio State University. I'm a second-year PhD student working in the network-based computing lab with Dr. DK Panda. And today I'm going to present our recent work about this topic, enhancing MPI for HPC clouds, a case study with Amazon AWS and Microsoft Azure. We are interested in this topic because recently we observed there's a dramatically increasing needs for high-performance computing clouds in the industry. And many companies like Microsoft, Azure, or Amazon AWS, they have already started some high-performance computing cloud services to their customers. And so we are wondering if we can use message passing interface in those HPC cloud systems, because MPI is a very popular programming model for traditional HPC, and we want to see how the MPI performance is going on those cloud systems and how we can optimize the performance in those cloud systems. So in the left-hand side part of this poster, we introduce our supports for MPI supports for both AWS and the Azure systems. And here we include some details with how we do implement MPI support and how we propose our new designs and use the features of different systems to get better performance. And after that, in the remaining part of this poster, we did show out the detail of our performance evaluation results, and people can also read from those performance evaluation to see which performance in which MPI library in which operation has a better performance. And I think that's very useful to HPC users. So let's first briefly go to some information about support for both AWS and Azure virtual machine. So for AWS recently proposed a new elastic fabric adapter technology, and it provides a new transport mode called scalable reliable datagram. It's similar to UD, but has some small differences. And you can see the full software stack here. And due to the characteristics of EFA and SRD, we have three main limitations: the number of SRD QPLs, and the data ordering, and the last limitation is the data transmission size limit. So for first QP limit, we use single QP to communicate with multiple peers, and that will reduce the number of QP in use. And there's also very low overheads for SRD to use this design. And second, for out of order data on receiver side, we use sliding window-based receiver design to handle that. And for large message transmission limits, we use zero copy running protocol to break down large message and transmit it to receiver side. And then this for Azure virtual machine support. We first did an in-depth performance evaluation, and based on the evaluation results, we did the performance optimization by adding InfiniBand support with details here, which basically improve the intra-node communication performance. And then we also did the point-to-point and collective tuning, and also choose the best neural mapping policy for the collective communication. We also cooperated with the Azure team to make MIPH2 as the built-in MPI library in their default CentOS HPC image. So the remaining part shows some performance evaluation of both systems. We did performance evaluation on both systems in benchmark level, MPI benchmark level, and then application level. So in MPI benchmark level of AWS, we see that small message size has very close performance in point-to-point. But for large message size, it starts to show some differences. SRD actually starts to show some benefits for large message sizes. And for collectives, we see the better performance for MIPH2 in most message sizes. and the application has the similar trends to collective performance evaluation results. On Azure, it's similar to AWS. We also did a performance comparison with MFH to optimized and non-optimized version, and also with another built-in MPI library in Azure system. So you can also see the details here. And if you have further questions, please feel free to contact us. And thanks here. That's all. Thank you.